Welcome to February 18th's LeetCode challenge. Invert binary tree. Given the root of a binary tree, invert the tree and return its root. So we're given an example of a pictorial of a binary tree here. And you basically want to invert it, basically flipping all left nodes to right nodes and all right branches to left branches. So therefore, if you have, say, a root binary tree as such, showing 4271369, then you will return 4729631. So a couple things here. If you want to visualize it, you have the root being the same, and you have this the offspring nodes here being flipped, and each of those leaves are flipped as well. So therefore, you want to basically invert it. And here's another picture here of a simple one. You have basically 213, it becomes 231. And then we have empty root, empty tree, then you return an empty binary tree. So the constraints of the number of nodes in the tree range between 0 to 100, and the value of each node is basically negative 100 to 100. So there's a couple ways to approach this. Let's do it recursively. So this is the classical tree problem that best suits a recursive approach for, with all type of binary tree type approach. You do it iteratively or recursively. Let's just do it recursively. So the algorithm, let's think of some ideas. The inverse of an empty tree is an empty tree. The inverse of a tree with root r is basically, and a subtree would be basically inverting the two offspring nodes or the children nodes. So basically, we want the tree of the root, whose subtree is on the right. You want to inverse that to the left, and the tree subtree that's on the right, you want to inverse it to the left. And the trees on the right, you inverse it to the trees on the left, you inverse it to the right. All right, let's go about doing that. So if root is equals to null, return null, or just return root, whatever, that works. Alright, that just takes the base case out of the way. Now you make a tree node, right, and I'm going to call invert tree on that, and I'm going to pass it root.right. Similarly, we're going to make another tree node here called left, and we're going to call invert tree, and we're going to pass it root.right and left. All right, and then we need to actually do the functions where we update root.left to be right. So basically swapping the roots, inverting the left and the right, and then do that right and equals assign it to the left. And then at the end of this, we want to return the root. Alright, let's run this. So basically what we did is we inverse an empty tree. Inverse of an empty tree is an empty, return null. If inverse of a tree of the root r and a subtree be right and left, so if the right subtree is inverse is left and the inverse of a left subtree is the right, and then we just return root, submit this. So time complexity wise, we have each node being in the tree is only visited once, so time complexity is big O of n, where n is the number of nodes in the tree. We can't really do better than that because we have to at least do every node at least once to invert it. And the recursion is of basically big O of each, where each the height of the tree. So the function calls will be placed in the stack to be the worst case scenario. So basically, space complexity is also big O of n. Alright, that's it. Have a great day, guys.